We'll go ahead and get started here. It's 5:15. So today we got a couple things going on. Logan's going to be giving a talk on reverse engineering, and then we're going to move into what we're calling Hack the Box night, I guess. And so we'll just get into smaller-ish groups and work on a VulnHub VM together. So practicing some pen test skills. And if we get stuck, we can help each other out. And I've actually gone through this box before, so I've got a write-up that we can reference if needed. So yeah, just a bit of a learning opportunity there. And then I believe you've got some interactive stuff as well with your presentation a little bit. Okay, so if you want t-shirts, they're $20. They can go to Logan in the back, Star Wars shirt. Nice, by the way. So $20 for the shirts, and I don't think there's anything else news-wise. So, yeah. All right, so I'll hand it off to Logan then.
All right. How do I get that to work?
You press buttons on the little screen up here.
Oh.
Or I guess next to the screen. There you go.
All right. So this is going to be a quick talk on reverse engineering and assembly. No. All right. So reverse engineering, why would you want to do it? You might want to understand malware. Malware researchers, security researchers are always doing that. You might want to determine if proprietary software is secure, or you might want to modify proprietary software. I don't know, like crack a program so you don't need a license or something. If you're nefarious, if you're a good guy, just evaluate stuff. And you might want to understand like how code works at a more deep level. All right, so there's in Linux, we use ELF files are the, here's this, there we go. ELF files are the executable and linkable file format. They are the standard executable format, and they have been since the 1990s. There's three types: relocatable files. Those are those .o files you make when you're compiling something that you will then link to a executable, and shared objects like libraries. So for example, ncurses. If you want to check what kind of file something is, you just type file and whatever. Put the name of your ELF there and it'll tell you. So an overview of an ELF file. It'll start with an ELF header, and then there's two other key headers, the program header table and the section header table. Now when you are looking at an ELF file from the view of like a linker, you're going to be using the section header table to determine what parts of the file you need to put together to make your executable file. When you're looking at it from like the view of execution, you're typically going to look at the program header table and load stuff from there. So that's what the ELF header looks like. There's a lot of things in there, but just some few things would be that eIdent string, the first thing you see there. It's going to have like, I think the first byte is like 7F. And then it'll say ELF. So if you view that in like a hex view, you'll be able to see that right off the bat. And then eType, that'll specify what type of file it is. Again, it might be relocatable, executable, dynamic, or it could be a core dump, just depending on what you have there. So there's a lot of things there. I'm not going to go over all of them. If you want to look up more of them, they're there. And then that's what the segment header looks like. It tells you like where to start execution from, that sort of stuff. And then there's the section header. So that's just sort of a general overview of what sort of data is there that you could look at. So if you want to look at all the code that's in an ELF file, you go objump D, and that'll give you all the code. It'll give you more than main. It'll give you like the start function and a bunch of initialization function that you don't really need if you're going to be disassembling something. But I don't know, there's always a chance that somebody could throw something in there and try to be tricky with you. Objump-X will show you what information is in the headers of those headers I just showed you. strace will give you any system call that a executable makes. ltrace will give you any call to a shared library that an executable makes as it's executing. And strings will just print out all the ASCII values of a file. And then here's what you can do with radar, I don't know how you pronounce that, to view, the first thing it does is it sort of evaluates the program, looks at the functions. You can hit S to seek to a place in the program, print the disassembled functions, or you can hit VV to view things in a visual format. So I'll switch and demo that now. So if I go, let's see, extras, IASG, reverse engineering. Just, if I look at this, program that I got from a YouTube channel called Live Overflow. It's a really simple license key checker. If you run it, you're supposed to give it a key high. That's wrong. If I want to look at it more, I can go R2, which will pull up radar, give it the, type that key in, and it'll start doing this. So if I go hit AAA, AFL, that'll give me all of the different sections of code there are. I can seek to main, and then what was it? Print the functions in it. With a PDF. And that'll give me a disassembled view of that function. Or if I want to look at all the functions that it might be calling, that's 2 capital V's, I think. What have I done? Oh no. There we go. That worked. And there's I don't know what that stuff is on the left there, but there's a view of all the functions that this I don't know. I don't know what I pulled up here. Whatever. Point is, you can get a process control flow graph using that. So going back to this. These tools are good for getting some information about a program, especially those first 5 I went over. But if you want to be able to actually see what's going on and really understand a program, you're going to want to learn assembly. So here's a quick tutorial of assembly. So that's a picture of a process. You have at high memory addresses the stack, which will grow down towards lower addresses. You got the heap below that, uninitialized data, initialized data, and text below that at the lowest address. So the stack is a first in, last out data structure. You're probably all familiar with it. You've probably all dealt with stacks. It grows towards lower memory addresses. So the top of the stack is at a lower memory address than the bottom of the stack. That's something somewhat counterintuitive. And it'll grow as you call functions, and those functions allocate local variables. And then when that function is done and it returns back to the other function, the stack will pop off stuff and go back, it'll shrink. The heap is below that. That's where you allocate data using malloc, calloc. It will grow towards higher memory addresses. So those will they actually can grow together, and you can get stack collision vulnerabilities from that. The uninitialized data, which is data that hasn't been initialized or is initialized to 0. Initialized data, which is global or static variables that are initialized. That's wrong. Okay. And then the text segment, which is where all your code is stored. So what do assembly instructions look like? They look like that. You have an instruction followed by some operands. So, and those operands are registers. So what's a register? You can think of them like variables that are pre-named and of a fixed size. The 64-bit instruction set includes elements from the 16-bit and 32 instruction sets from Intel. So if you want to learn 64-bit instructions, it's best to view those first. So this is the 16-bit registers. There's obviously AX, BX, CX, DX. Those are your general purpose registers. The stack pointer, which will always point to the top of the stack. The base pointer, which will point to the bottom of the stack frame, or the top of the stack frame. The source index and the destination index are used for like string operations and best practices, and the instruction pointer, which points at the current instruction that's executing. So you don't really have to worry about the segment registers. They're used for like segmented memory, which nobody really uses anymore. And one caveat is that registers SI, DI, BI, or BP, and BX are all expected to be preserved by a function that gets called. So once that function returns, they're all expected to be the same. So x86 registers are pretty similar. What they've done is they've stuck an E to the beginning of most of the registers, and then they've made them 32 bits wide. So you got EAX, EBX, ECX, EDX, ESI, EDI, EBP, and ESP. And the lower 16 bits can still be addressed as you normally would with AX, BX, CX, and DX. And then we get 64-bit registers, which are like the similar to the last one. They've just extended most of the registers to 64 bits and gave them a new letter at the beginning. So now it's RAX, RBX, RCX, RDX. In addition, they added 8 more registers for general purpose, like computing. So those are R8 through R15. So to address the lower 32 bits of those last 8 registers, you use the word D, and that's means D word, or double word. A word is 2 bytes. To address the lower 16 bits, you use W, which is a word, right? So this is a simple assembly program. It returns 35. That's all it does. It's the same as this. And that's because typically, here, I'll go back to this. When you want to return something in assembly, what you're going to do is you're going to put that in the RAX register or EAX, depending on what architecture you're running on, and then return back to the function that you previously called, that called you. So there are thousands of x86 or 64-bit assembly instructions out there, but 90% of code is like the same 13 or so instructions. So if you can, it would take a long time to master, but you can get a pretty good grasp of it pretty quickly. So there's a few key instructions, or move, which just moves things from the argument on the right to the argument on the left. And you can move between registers, memory and registers, in any order you want. And you can move a const to memory or a const to register. Now you can't move from memory to memory. You have to bring something into a register first if you want to do that. There's push, which will take an operand and stick it on the stack, and then decrement the stack pointer by 4 and place that value at the current stack pointer. So you got to remember that the stack grows down, so decrementing increases the stack and makes it larger. There's pop, which will take the contents of whatever the stack is currently pointing at, pop it off, store it in whatever register or piece of memory you give it, and then increment the stack by 4, the stack pointer. You got call, which will it pushes the current code location onto the stack and then jumps to the code location indicated by that operand. It's pretty simple. And return pops a code location off the stack and jumps to it. Then you got leave, which will copy the frame pointer into the stack pointer. It'll pop a value off the stack and store it into the base pointer. And then it's usually followed by a return statement because you're generally leaving a function at this point. So here's an example of a function call. So you've got push, I guess on the left there's main, on the right's the function that's being called. So first thing you have is these 2 instructions that you'll see at the beginning of most any function. Push the base pointer onto the stack, move the instruction pointer to the base pointer address. Subtract 10 from the current instruction pointer. And then here we're moving these 2 addresses, which are the 2 arguments we've given to the main function of our program. We're moving those onto the stack. And then we set EAX to 0. We call our other function, right? And that will do that same first 2 instructions where we push the base pointer, move the instruction pointer to the base pointer, and then we set EAX to 4C in hex, which is like 35, 37, I think. And then we pop off that base pointer and we return. So what's that done is that's just returned 35, 37 to the program, right? And then we exit our main function. We move EAX to 0 because we're going to return 0 here. We leave and then we return. So that's the basic. That's a really fast course on assembly. And then there's a few ways you could obfuscate binaries. You could strip it, which will remove comments and that sort of stuff from it. There's ways of using like ptrace and stuff to detect if your program is currently being run inside a debugger. You can get around that by preloading stuff. And there's the move instruction is actually Turing complete, meaning you can write any program in just moves. So there's actually a piece of software out there right now that you can compile most any C program with, so long as it doesn't use too many floating point computations. And it will compile it entirely in moves, and that's a pain to reverse engineer. So that's about all I got. Thanks.